So I've got a few terms to go through from Chapter 8 of our Chang AP textbook before we jump into atom radius. So what's the atomic sizes by period and by group, and then we'll do ion size, looking at period and group trends. So we've talked about valence electrons. I want to get that formally in your notes. The valence electrons are the outermost electrons. They're going to be really important when we get to chemical bonding. So if we looked at something like lithium and looked at its electronic configuration, it's the third atomic number, so there's 3 electrons. So we have 1s2 would be the first 2 electrons. Then we have to jump to the second energy level and 2s1. The valence are these outermost electrons. The outer energy level that's starting to be occupied is 2. Okay. Core electrons are all the non-valence. Okay. So the inner ones, those would be the 1s2. Removing valence electrons is often doable at room temperature. If you take lithium metal and put it in water, that valence electron will pop right off quite quickly. Group 1s are very reactive. Those core electrons take incredible amounts of energy. You can remove them, but not in a chemistry lab. Okay, maybe with a laser, you could possibly get a core to move. So huge energy differences. Okay. Moving on, representative elements. This is a new term. This hasn't come up yet. It is elements with unfilled s and p orbitals. So when we start at group 1a, so the A system doesn't count the transition metals. It just counts the s and the p blocks. So 1a hydrogen, 2a lithium, 3a boron, 4a carbon, 5a nitrogen, okay, all the way up to 7A is our representative elements. When we get to 8A, they're all filled up. So that noble gases are not representative elements. Okay. So this makes a fairly easy test or quiz question. You know, which of the following is or is not a representative element? So calcium, atomic number 20, would be. Okay. Iron would not. Okay. It's in the D block. Selenium would be a representative element. Xenon, atomic number 54, would not. Okay. Now, probably the most important on this slide, isoelectronic. This is going to come up all the time through our lesson on atom size comparisons and particularly ion size comparisons. 2 species with the same number of electrons and therefore the same electronic configuration. And we'll look at a couple examples. So I'm using some nuclear notation. We're going to compare hydrogen 1. Okay. The 1 is the mass number versus helium 4 or helium ion 4. Hydrogen, doesn't matter what the mass number is, it has 1 electron when it's neutral, so its electronic configuration would be 1s1. Helium isn't normally charged, but it is possible, and I'm using the charged helium. Helium normally, you would expect it to have 2 protons and 2 electrons. It always has 2 protons, but it's normally neutral and has 2 electrons. But I'm doing the charged helium that's positive, that's lost 1 of its 2 electrons. So when helium is plus, it is also 1s1 because it only has 1 electron. So you would say that the hydrogen atom and the helium plus ion are isoelectronic with each other. They have the same electronic configuration. My second example, we're going to start with calcium 2 plus, and then think of some of the species that would be isoelectronic with it. There's a fair list. It's more than one. So calcium plus, let's run through all the electrons. So calcium atomic number 20, so 20 protons. It would have 20 electrons if it was neutral, but when it's positive, it's lost 2 electrons. It only has 18 electrons. Now I'm going to do out the electronic configuration the long way. We're going to build up, starting with the lowest energy level, 1s2, 2s2, that's 4 electrons, 2p6 will get us up to 10. So we're kind of at neon. We're not at 18 yet, 3s2, 3p6, that's all the way up to argon. And we have 2, 4 plus 6 is 10, 2 more is 12, 6 more is 18. We just finished. We got all 18 electrons in calcium. So now what else would have 18 electrons? Well, the most obvious would be something neutral with atomic number 18. So argon, when it's neutral and has 18 protons and has all 18 electrons, would be isoelectronic with it. But there's some other charged species that also have 18. Let's look at atoms that have less than 18 that you could add to. So less than 18 would be chlorine, only has 17. But chloride, chlorine, when it becomes minus and gains an electron, it would also have 18. So chlorine is 17, chloride is 18. If we went to sulfur, it would normally have 16, but sulfur as an ion is 2 minus, gain 2. 16 plus 2 would also be 18. So argon, chloride, sulfide, all isoelectronic. Phosphorus also can be isoelectronic. When it's neutral, it's got 15, but when it becomes an ion, 3 minus, 16, 17, 18. And that's about it. When you get to silicon, it doesn't want to become 4 minus. Okay? We find that group 4A only likes to share electrons. It doesn't form ions. If we go after argon, we already did calcium losing 2. Potassium would have 19 when it's an atom. So it's got to lose 1 to go 19 down to 18. So potassium plus would be isoelectronic. Okay. I'm going to stop there, but you could start working into the D block. If scandium, we already saw scandium 3 plus in one of our homework questions. That'd be isoelectronic. Titanium, if it became 4 plus, I'd have to double check whether that's possible or not. Your data table has it, or vanadium 5 plus. Now, copper, atomic number 29, you're not going to have copper 11 plus. Okay, so you can't keep going on forever. There's a limited number of isoelectronic species. Okay. So we're going to use these concepts, core, valence, representative, isoelectronic, as we work through a few topics. So atomic radius is first up. We're going to talk a little bit about charge, what's kind of pulling things together, and we'll use that principle to figure out size. So I'm starting with nuclear charge. So that's just the charge of the nucleus. That would be our Z letter. our atomic number. So what's the charge of the nucleus in helium? It's atomic number 2. So for its 2 protons. Now what really matters to size is a concept called effective nuclear charge. Okay? What does an outermost electron feel? Because an electron way on the outside, a valence electron, isn't going to feel the full charge in the middle. There's lots of things between the outside and the very middle blocking. So we're going to look at what does an outer electron feel, or what's the effective nuclear charge for an outermost lithium electron. So I started with the nucleus that would have 3 protons. The neutron count wouldn't matter. Neutrons would not affect what an electron would feel charge-wise. So it doesn't matter what isotope we have. So I'm not going to put in a neutron count. We're going to have a first energy level, and lithium has a second energy level. The third, n equals 3, has no electrons in it, so I'm not going to draw that. I'm going to use kind of some of our Bohr type labeling. The first energy level holds 2 electrons. Maybe way back in grade 9 or 10, your science 10 teacher might have drawn those together. Hopefully they did. That's because they're in the same orbital. That's 1s, 2 electrons. Then we've got 1 more electron on the outside. That is our outermost electron. Effective nuclear charge is what does that outer electron feel net. So I'm going to recolor code that. I'll make that one red. Our chords are green, our valence is red. So what we really care is about Z effective. Okay? That would factor in the 3 protons that are attracting. But then we've got those 2 green electrons. We've got 2 electrons that would be repelling the red electron. Z effective factors in the 3 protons pulling and the 2 electrons repelling. Now, we're not going to look up any Z effectives. Okay. Z effective nicely scales with the charge in the middle. So what we're going to use, the charge in the middle is proportional to Z effective. Okay. Proportional, okay. If one goes up, the other goes up. So we should be using Z effective, but we're going to just use the charge in the middle as a proxy. So if we're comparing hydrogen and helium, hydrogen has a Z of 1, helium has a Z of 2, and that's really all we need to know. There's going to be a greater pull on the helium outermost electrons than the hydrogen with double the Z. So let's look at group trends, which is easier, and then period trends where I need to slow down a little bit. So atomic radius. So what is it? Half the distance between 2 atoms. If we think of just one atom, and we've got our energy levels, and we're trying to measure the radius, we can actually do that with one atom. Electrons, we can't know where they are. We've got the Heisenberg uncertainty principle. They're waves, but they got average distances. So that is in theory would work, but in practice it doesn't. But if you have maybe a diatomic element, if you have Cl2, and you've got 2 nuclei, okay, We don't know exactly where the electrons are in between the two, but if you measure the total distance between two of them, okay, and then you figure out the radius, would be just half the distance between the two. So we can't measure where electrons are, but we could measure where two atoms are and just half the distance between the two. So that's the main way you can measure the radius of an atom. So let's look at some trends in a group, or going down a group. I'm going to use group 1, or 1A, our alkali metals. So our first atom is hydrogen in group 1. We've got one proton in the middle, and we've only got one electron. Our electronic configuration is 1s1. I'm going to do a couple next members, and then we'll talk about the trends. The next down in the group would be lithium, and then I'll do sodium. So lithium has 3 protons, and then we get to sodium with 11 protons. Now, I'm not drawing these to scale because I'm trying to get things to fit on my smartboard. So for lithium, there's 3 electrons. So we're going to fill up the first energy level, and then I'm going to need a second energy level. So we've got 2 valence electrons, sorry, 2 cores and 1 valence. So in lithium, it's 1s2 is our 2 cores, and then 2s1 is our valence. We've added an energy level. I'll do sodium and then talk about the trend. Maybe you've picked it up already. Sodium is now in the 3rd period of the periodic table, and we need 3 energy levels. First energy level holds 2 electrons. That's our 1s2. Second energy level holds 8. 1, 2, 3, 4. Those would be kind of all spin-ups. 5, 6, 7, 8. If you ever wondered why in Bohr you went and put 4 pairs, it's because you've got 2s2, 2p6. There's 4 orbitals in total, and that's why we put 4 pairs in the Bohr model. But sodium has an 11th. We need 1 more, 3s1. So we see this S1 as the ending for all of our group 1 elements. But the difference is 1 energy level to 2 energy levels to 3 energy levels. So what's going on in terms of size in this group or any group? As you go down, they're going to get larger because of energy levels that are filled. So I'm not going to draw out the halogens in group 7A, but fluorine would be the smallest, chlorine bigger, bromine bigger, iodine bigger. Okay. Same would be true for noble gases. They get bigger as you go down. There's 1 more energy level every time you go down. Okay. So that's something hopefully straightforward. You're not even going to draw elements. You're just going to look. If I ask you to compare calcium versus beryllium on a test, you're going to notice beryllium is in the 2nd period, calcium's in the 4th, so calcium's bigger. No need to draw anything. You don't need any quantum mechanics to answer that. We're going to get a little trickier. This is where effective nuclear charge is going to come in. we're going to look for period trends now. So we're staying in the same energy level. I'm going to draw 4, not all of them, across period 2. So I'm going to do lithium again, boron, nitrogen, and neon. And then we'll talk about what is going on. Is it staying the same, bigger, or smaller? So lithium, 3 protons, boron, 5 protons, nitrogen, atomic number 7, so 7 protons, and then we get to a noble gas, 10 protons. Every one of these elements has the first energy level filled. So I'm going to do that. Put in a first energy level and then go back and fill in the 1s2 electrons. Okay. We don't spread these out because they're a spin up and spin down in the same orbital. Second energy level with 4 orbitals that holds 8 electrons. Okay. To get the valence electrons, we just start in the period and count over. It'll tell us our valence. So lithium's the first element. It has 1 valence. Boron, the boron atom, is the third element over. Okay. Just counting representative elements, lithium, beryllium, boron. So there's 3, 1, 2, 3 that all be spin up. We filled 3 of the 4 orbitals. We move on to nitrogen, which is the 5th over, group 5A. So we've got 4 atomic orbitals. There's 1 electron, 2, 3, 4. We've gone spin up and all, and there's the 5th spin down. Neon, we're all the way across. We're 10 across. 8 valence across, 10 in total. So 1, 2, 3, 4, 5, 6, 7, 8 for group 8A. So the 2 concepts for answering any of the atom or ion size, one of them is going to be the number of energy levels, and the other one is going to be Z or Z effective. Okay, and they're the same. What's pulling the outermost electron in? Okay. So in our group trend, the energy level was what kicked in first. There was a total difference in energy levels for our group, going up or down a group. For going across a period, the energy level is the same. So we want to look at Z effective as we go across the group. We're not going to see a big size difference. If we start at lithium and think of what is pulling the red electron, there's 3 protons is all we have to pull in that electron. If we move to the other extreme of the period and we get to neon, 1 outermost electron has 10 of protons pulling it in. 3 to 10, that's more than a triple. There's over triple the protons pulling in on a neon valence electron compared to lithium. So if we think of the second energy level for neon, it's got a greater pull on that energy level, so that's going to pull it closer. A greater pull would not repel. Protons aren't going to repel those electrons, they're going to shrink it. So the trend going across is that Z effective is increasing. So in terms of size, we're going to have bigger lithium, 5 protons pulling in on boron, 7 pulling in on nitrogen, and then we get to neon, it has the greatest pull and the smallest size. So the smallest is actually the neon. The largest is going to be our lithium atom. There's the trends. Okay. So a nice graphic of our trends. It's not perfect, but if we look at atomic number and size, as we go across, this is period 2. We pretty much have a perfect trend from lithium across to fluorine. Okay? The noble gases aren't included on this graphic. Okay? It's getting smaller and smaller from lithium to fluorine. Okay? If we look at period 3, pretty much the perfect trend again from sodium to chlorine. When we go to period 4 in our table, not perfect. From potassium to bromine, we've got some quirkiness, and it's caused by some of our D block transition metals. Okay? Some more complicated things are going on, but still a pretty good trend going on. Okay? And as you keep going, again, the trend mostly works, but there's some exceptions. Okay? But our period 2s and 3s, we get a nice perfect trend using Z effective to predict the size. Okay? And it's fairly significant. Sodium around 200 picometers. Pico is 10 to the minus 12. So even smaller than that nano prefix we use. 200 to under 100. So chlorine is half the size that sodium is. So that Z effective is pretty powerful. Last concept, ion radius. So everything's been neutral so far. We're going to look at cation size, and then we'll look at anion size. So first, a little bit about cations. Okay. And a trend, cations will always decrease in size when electrons are lost. So we'll get some visuals pretty soon. Okay. We're going to keep looking at lithium because it's our first metal. So we have 3 protons. We've got 2 energy levels, 2 cores, and a valence. This is going to be our comparison, 1s2, 2s1. And then I'm saying when this becomes a cation, it's always going to shrink. So let's look at lithium plus and then try to figure out why this is true. Okay. Everything in the universe that is a form of lithium is 3 protons. Okay. Atomic number has to be 3. Proton count has to be 3. But lithium plus doesn't have 3 electrons anymore. To become positive, it's lost an electron. So lithium doesn't have 3 anymore. It only has 2. It's lost its valence electron. So its electronic configuration is 1s2. Okay. So why would lithium plus be smaller than lithium metal? Well, your first default was that list that we saw on the other slide. It didn't mean a lot to you yet, but it will slowly start meaning more. You want to start thinking of energy levels first. If that's a tie, then you're going to look at effective charge. But the energy levels are different when we talk about atoms to cations. Lithium has 2 energy levels. Lithium ion only has 1. So we went from 2 rings down to 1 ring. Okay. So this is going to be smaller. It's got a whole less energy level. And you see this for all of our cations, whether it's lithium plus that empties the second energy level, beryllium 2 plus would also lose all the electrons in its second energy level. Okay. Calcium 2 plus would lose all the electrons in the 4th energy level. So it'd go from 4 energy levels down to 3. So there's always a shrinkage for cations. Anions kind of do the opposite. They're gaining electrons, extra electrons to repel each other a little bit more, and they want to get a little further away from each other. So we're going to see a bigger anion compared to the neutral atom. So I'm going to look at nitrogen versus nitride, nitrogen 3 minus. So in period 2, I don't have a lot of room to write the nucleus. I'm going to leave out the charge, the proton count, and just put a dot to simplify my diagram a little bit. Okay? But both of these, what I'm leaving out is the fact it has 7 protons. Okay? Nitrogen, the first energy level is filled, the second is not totally filled. So that's the 1s2 for the atom and the ion. Time to do valence. Nitrogen is in group 5a. So it has 5 valence electrons. 1, 2, 3, 4, 5. Okay. One of those electrons has 7 protons pulling it together. Nitride 3 minus went from 5 to 6, 7, 8 when it became 3 minus. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Energy levels are a tie. So then we're going to look at what's the outside to the inside. The proton count is a tie. So there's the same 7 protons in nitrogen and nitride trying to pull things in. So that's a tie. The difference is more electrons. This is 1s2, 2s2, 2p3, 1s2, 2s2, 2p6. We've got more electrons. So we have an energy level before. We pump 3 more electrons in it, which more electrons to the same positive is just going to repel each other a little bit more. So when you pump more electrons in, it's going to expand as they repel each other. Okay. More electrons, more negatives in the same space. They're waves, but they're still in similar space, and they're going to repel and make it bigger. So this is larger because of those extra electrons compared to the atom. So cations shrink because there's 1 less energy level. Anions expand because there's more electrons repelling each other. We have a little bit of a visual that I took from the textbook. You don't necessarily have to write this in, but if in your notes, but if you have a lithium atom and a fluorine atom, both neutral, you have their relative sizes. The cation, when you make an ionic compound, is going to shrink because it lost energy level. So you see the gray metal shrinking in size. The fluorine, when it gains an electron, it's going to get bigger, and you see the green ball increasing in size. And that's always what we get. This would be ionic bonding, cation shrink, anion expanding. We're going to look at trends across the whole period, and then we're done for this lesson. Now, this is the trickiest part because we have to think of it as 2 different camps, 2 different areas. If we go across period 2, we got cations shrinking, and then you got anions expanding. It's not a consistent trend. We're losing electrons in the S block, and we're gaining electrons on the far right-hand side of the P block. because we got metals at the beginning and we got non-metals at the end. Okay, we're not going to deal with the metalloids. So I'm going to stick to period 1. So we got lithium, beryllium, boron. I'll look at those losing electrons. So lithium plus, beryllium 2 plus, boron 3 plus. Three protons for lithium. Beryllium is 4 protons. It's atomic number 4. Boron's atomic number 5. I'm writing the protons in now. They're different. It's important to have that visual. Lithium would normally have 3 electrons, but it's lost 1. So lithium atom would have 3 electrons. It's positive. It's lost 1, so it's only got 2 electrons. I'll keep my colors. I've been using green for quark and throughout the lesson. Beryllium would have had 4 electrons as an atom, but it's plus 2, so it's lost 2. It's also down to 2. We got 2 isoelectronic atoms. If we move on to boron 3 plus, okay, boron, the atom would have 5 electrons, becomes 3 plus. We're isoelectronic. Again, we have 3 isoelectronic ions. So what's going to happen in terms of size? So we're heading across period 2. We're 3 across. The energy levels are the same, so we're not going to look there. We're going to look at what's going on between the outside and the inside. Okay? The electrons are also the same. They're a tie. The difference is 3 protons to 4 to 5. So as we go this way, and Z effective is going up, what does more charge do to the size? Does more charge blow it apart or pull it together? And we're going to see it shrink or pull together. So as we head across, those more protons are going to cause it to shrink. So I'm sort of doing just bigger arrows throughout this lesson, so they're going to get larger with a smaller charge. So lithium would be the biggest, beryllium 2 plus a little smaller, boron 3 plus the smallest still. Okay. So we're starting to repeat some of our logic. Okay. Basically 2 logic statements. 1 is energy levels determining size. 2 is charge from the outside to the inside. Let's keep going across the group. Now, carbon doesn't ionize. Group 4, carbon and silicon are the heart of sharing, not ionizing. And we're not going to look at noble gases, nitride, oxide, fluoride. Okay? We're going to see a big jump up in size because these are anions that are getting way bigger than those small cations. I want to write in the proton count because it's changing. Nitrogen has 7 protons, 7, 8, and 9. Okay. So we have the same type of trend. Effective nuclear charge is going up. We have 2 energy levels, not just 1. Like we did in the first part of the period. All of these have their 1s filled. Nitrogen would, in 5a, group 5a would have 5 electrons, but becoming 3 minus, it gets its 6th, its 7th, its 8th. It's got a full outer energy level. So from boron 3 plus to nitride, we got an extra energy level, way bigger. Oxygen in group 6A would have 6 valence electrons, minus 2 brings it also up to 8 valence. So nitride and oxide are isoelectronic with each other. Fluoride goes from 7 to 8 valence from the atom to the ion, also isoelectronic. So we see the exact same pattern again after a big jump in size. Z effective is continuing to increase, okay? But we're in a bigger energy level. So what does that do to size? We have 3 isoelectronic anions. So that's going to cause them to shrink as we go to the right. So the largest is on the left. And across every period of representative elements, we're going to see this same type of trend. The cations get smaller, jump way bigger to the anions, and then they decrease. But you have to realize there's that big jump in size from 1 to 2 energy levels. So if you think of going across a period, atomic number versus size for our ions, we're going to see the cations decrease in size. Then we're going to jump to our anions, which are way bigger, and then they're going to decrease in size. I just want to highlight there's that 1 energy level versus 2 energy level difference between the cations and the anions. So we're mostly through chapter 8. Okay. The next lesson is going to talk about losing electrons. Same type of principles are going to come up. To lose electrons, we want to have something maybe really big, really far from the nucleus, and a lower Z effective would allow an electron to be lost easier. Okay. But we need to practice these skills.